Hi guys, in today's video I'm going to go over some paper 2 specific topics for IGCSE Edexcel chemistry. So we're going to start by looking at gas volumes. So you could get a question like this: 2.7 grams of calcium carbonate reacts with hydrochloric acid. Calculate the volume of carbon dioxide produced in centimeters cubed. So first of all, you need your balanced symbol equation. So calcium carbonate plus hydrochloric acid forms calcium chloride plus water plus carbon dioxide. And remember, I know the formula because I know that calcium is Ca2 plus, carbonate is CO3 2 minus, which is why the formula is CaCO3. For calcium chloride, it's Ca2 plus Cl minus, so the formula here is CaCl2. And you must learn the formulae of the common acids and things like water and carbon dioxide. Anyway, let's get down to doing the actual calculation. Now remember, it's essential that this is a balanced symbol equation, so I'm going to put a 2 here and then I'm going to double check that everything else is balanced. Yes, it is. So to solve this, I'm going to use my favourite table, which states that mass MR, number of moles, goes along here. We're using this formula triangle. Mass is MR times number of moles. So input into the table the information you have. So that's 2.7 grams, and we're after the volume of carbon dioxide. So the MR of calcium carbonate is 40 plus 12 plus 3 lots of 16, which equals 100. So the number of moles is mass divided by MR, so 2.7 divided by 100, which is 0.027. Now check the mole connection. It's 1 to 1, so we can just steal that number of moles and put it here. Now you need to remember this, that 1 mole of any gas occupies 24 decimeters cubed of space effectively. So we have 0.027 moles, so you times that by 24 to get 0.648 dm cubed, but remember that the question asks for it in centimeters cubed, so simply multiply that by 1,000 to get a volume of 648 centimeters cubed as your final answer. The next type of calculation you need to be able to do in paper 2 is titration calculations. They'll always look something like this. So 25 centimeters cubed or 0.2 mole dm to the minus 3 sodium hydroxide reacted with 28 centimeters cubed of hydrochloric acid. Find the concentration of hydrochloric acid. So this is a volume, this is a concentration, here's another volume, and we're after concentration. In this case, we need this formula triangle, which states the number of moles is concentration times volume. As always, we need a balanced symbol equation, so that's sodium hydroxide plus hydrochloric acid forms sodium chloride plus water. Double check to see if it's balanced. Yes, it is. And remember, this is a neutralization equation. So number of moles, concentration, volume goes down here. So what information have we been given? Well, we know that we have 25 centimeters cubed of sodium hydroxide. This needs converting to decimeters cubed, so I'm immediately going to divide by 1,000. We know the concentration is 0.2, and then we've got the volume of hydrochloric acid, which is 28 centimeters cubed, which again I divide by 1,000. So at this point we can see that we can work out the number of moles of sodium hydroxide by doing 25 divided by 1,000 times 0.2 to get 0.005 moles. Check the mole connection, it's 1 to 1. So we're allowed to copy that number across here. And then the last thing you have to do is do 0.005 divided by 28 over 1,000, because to find the concentration, you do number of moles divided by volume. And once you put that into your calculator, you get a value which is 0.179 moles dm to the minus 3. So that is your final answer, your final concentration. So let's look at electrolysis now. So remember, the definition of electrolysis is that it is breaking apart a substance using electricity. And the crucial thing here is that it needs to be a molten ionic compound. The reason it needs to be molten is so that the ions are free to move. Let's look at a few definitions. So the cathode is the negative electrode, and it attracts cations, which by definition must be positive ions because they need to be oppositely charged. Then you have the anode, which is the positive electrode. It attracts anions, which therefore must be negative ions. So you have this sort of situation where you have the electrodes dipping into a solution. So here's your beaker. And then they're connected to a power source. So here's your cathode. And here's your anode. Now, what are the rules for working out which ion goes where? So first of all, at the positive electrode, so the anode, this is the order in which the ions discharge. So halogens always win. So if a halogen is present, it will win. And after that, it's oxygen. At the negative electrode, so the cathode, the rule you need to remember here is that the least reactive element wins. So let's take a few examples. So what about aqueous sodium chloride? Well, look, in solution you have sodium ions, chloride ions. Because it's aqueous, you'll also have hydrogen ions and OH minus, hydroxide ions. So let's look at the sodium and hydrogen ions first of all. Well, according to this rule here, the least reactive element wins. So from the reactivity series, you should know that hydrogen is less reactive than sodium, so that will win. So I'm just going to write the equation now for its formation. So you take hydrogen ions, they're going to form hydrogen molecules, because remember hydrogen is a diatomic molecule, which means you need 2 hydrogen ions. In order to balance it, you need to add 2 electrons. Because you've added electrons, it means that reduction has taken place. And don't forget oil rig to help you remember this. Oxidation is loss of electrons. Whereas reduction is gain of electrons. Okay, so now looking at the chloride ions and the hydroxide ions, according to this rule, halogens always win, which means that chloride, being a group 7 element, wins. So we're going to write chloride ions forming chlorine molecules, so you need 2 chloride ions. And then in order to make that neutral, we need to minus E minus. So you can either write that here, or you can add them on this side. And because you've lost electrons, it's oxidation. So the reason we carry out this process is because hydrogen makes a good fuel and is used to make margarine. Chlorine is used to make bleach and disinfect swimming pools. And the leftover sodium hydroxide in solution is used to make paper. So let's take another example now. What about copper 2 sulfate solution? So let's work out what ions we have. Well, we have copper, the sulfate ion. Because it's in solution, we have hydrogen ions and hydroxide ions. So looking at our rules again, at the cathode, the negative electrode, then the least reactive element wins. So out of copper and hydrogen, that will be copper. And then at the anode, halogens win, otherwise it's oxygen. Now, there are no halogens here. We've only got the hydroxide ions, so that will discharge to produce oxygen. So let's look at our 2 half equations. So copper goes to solid copper. So we need to add 2 electrons, which means reduction's taken place. And then this is quite a complicated equation, but we're going to form oxygen plus 2 lots of water plus 4E minus, and you need 4 hydroxide ions in order to balance that, and oxidation has taken place here. Let's touch on exothermic and endothermic reactions now. So an exothermic reaction releases heat energy. Now you must be prepared to draw energy profiles. So we're going to label this as energy. This is the progress of the reaction. Now, because the enthalpy change is negative, it means that the reactants need to start at a higher energy compared with the products. Now, the difference between their two energies is known as the energy change or the enthalpy change, so we label that delta H. And then in terms of labeling the activation energy, well, it's the distance from the reactants to the peak. And remember that the activation energy is the minimum amount of energy required for a reaction to occur. They could ask you to draw how a catalyst would affect this. Now remember that a catalyst works by lowering the activation energy, so you just need to draw a little peak which is slightly lower and label that activation energy with catalyst. So how about endothermic reactions now? So these take in heat energy. Delta H is positive. Have the same axes label. The reactants again come first, but because delta H is positive, it means that the products need to be at higher energy. So the difference between their two energies again is delta H, so enthalpy change. This time, to draw the activation energy, you need to draw it like this. So this, therefore, is the activation energy. And then again, if they ask you for what it would be like with a catalyst, you just need to lower that peak. And then one tiny extra detail is to know that exothermic reactions are bond-making reactions. Whereas endothermic reactions are bond-breaking reactions. Now we're going to touch on chemical equilibria. So we often call this dynamic equilibria, and remember that the characteristics of a dynamic equilibrium is that the forward and reverse reactions occur at the same rate and the same time. And that the concentrations of reactants and products remain constant. This is an important arrow, which means that it is a reversible reaction. And I'm now going to talk you through some examples as to how we can alter the position of the equilibrium to increase or decrease the yield. And I'm actually going to use the Haber process to demonstrate this. So in the Haber process, we've got nitrogen reacting with hydrogen. Here's your reversible arrow forming ammonia. Now I need to tell you that the forward reaction is exothermic, which means it gets hot. So how can we increase the yield and why? So increasing the yield of ammonia is all about producing more ammonia. So the first thing we can do is decrease the temperature. The reason for this is because the forward reaction is exothermic, which means it gets hot. Now in dynamic equilibrium, what's happening is the reaction's always trying to oppose the change you make to it. Now people often struggle with this, but if you can simply remember that exothermic reactions get hot, so in order to favour an exothermic reaction, you want to cool down the reaction vessel. So we want to decrease the temperature. Why? Because the forward reaction is exothermic, and that is enough. So we're going to say the position of equilibrium shifts to the right. Now we need to look at pressure. So we've considered temperature. Well, how about pressure? Now here you want to count the number of moles of gas each side of the equation. So that's 1, 2, 3, 4. So there's 4 moles on the left hand side and there's only 2 moles on the right hand side. So we can see that when the forward reaction occurs, we produce fewer moles of gas, which means that there is less pressure. So how can we encourage it? Well, we could encourage it by increasing the pressure. And so in order to write this, we write increase the pressure to increase the yield. Why? Because there are fewer moles of gas on the right hand side. And therefore the position of equilibrium shifts to the right. Notice that catalysts have no effect on yield. That's so important that you know that. All they do is increase the rate of both the forward and reverse reactions by an equal amount. Now we're going to look at some organic chemistry, starting with the alcohols. So they have this functional group, which is OH. So we're going to look at the first, second, and third alcohol. So we're going to use monkeys eat peanut butter to help us remember their names. So the first alcohol is methanol. So monkeys eat ethanol, peanut, propanol. When it comes to drawing their displayed formula, make sure you have that functional group and then complete by remembering that each carbon atom forms 4 bonds. Looking at the carboxylic acids now, they have a slightly different functional group, which looks like this. So, doing the same thing, looking at the first 3. Monkeys eat peanut butter, so the first one is methanoic acid. Monkeys eat ethanoic acid, peanut, propanoic acid. So first of all, start by drawing that functional group and then count up how many bonds around the carbon. Well, there's 3. Complete by drawing the 4th. Now we need 2 carbons. Let's draw the functional group and then just complete the rest of the molecule. For propanoic acid, it's exactly the same. So now we've built up how we draw our alcohols and carboxylic acids, we can now dive straight into esters. So with an ester, you've got an alcohol reacting with a carboxylic acid. It's a reversible reaction and it produces an ester and water. Notice that this is a condensation reaction. So let's take an example such as ethanol. And we're going to react it with methanoic acid. So notice that we need to lose a water molecule. So we lose the OH from the carboxylic acid and the H from the alcohol. And then you effectively pop them together. So you combine those ends to get this structure. And notice that this is the functional group of the ester. And we've made H2O as a byproduct. So naming the ester now. Now the first part of its name comes from the alcohol. So in this case we had ethanol. The second part of its name comes from the acid. So we had methanoic acid. So what have we produced? Well, according to the alcohol, we'll have ethyl. And then according to the carboxylic acid, we'll have ethyl methanoate. And remember, you need a strong acid catalyst to catalyse this. I think probably the hardest part of the specification is looking at polyesters now. So in this case, we're going to be using ethane dioic acid and ethane dio. Now let's try and draw them. Notice that it's ethane, so we're going to have 2 carbons, and then we've got a carboxylic acid, which means we have this functional group. But because it says dioic, it means there's 2 of them, which is why we make it symmetrical and draw that carboxylic acid functional group on both ends. So that's how you draw ethane dioic acid. Then ethane diol, I think I'm pronouncing that wrong. We've got an alcohol, which means we have an OH functional group. There's 2 of them, and then we've got that ethane as well. So 2 carbons effectively with 2 alcohol groups at each end. So 1 at each end, and then complete, making sure that each oxygen has 2 bonds, each hydrogen has 1 bond, each carbon has 4 bonds. So once you've done that, you can now work out where you're going to lose the water molecule from. So you're going to lose the OH here, the H here, and then you're going to stick together the ends. The hardest thing here is to realise that you're going to have square brackets. And because effectively you're joining loads of these together, you have a long bond here which connects to the first carbon of the ethane dioic acid. Then you connect it to the second one. We know that we've lost the OH group that I've highlighted, and so therefore we need to stick it to the O of the alcohol. And then just complete the rest of the molecule. And then again, because it continues the other side, we elongate the bond on the other side. And because we don't know how many we're joining together, we use N to represent that. Right guys, I hope you found that helpful. Don't forget my video containing paper 1 and 2 has absolutely everything you need. This was me going over the most important parts of the paper 2 topics. Let me know how it goes. I hope you're having an okay exam period. You're nearly done, so congratulations over that. And yeah, just let me know how it's all going.